And now that we know that the driving field is generated by surface charge layers, and we have some idea about how those surface charges are distributed, we can ask what happens at a change of medium, such as here, like what if electrons coming in through a copper section of wire transition into a section that's iron or tungsten, and then maybe back into another copper section there. So what of our various variables describing the scenario change or don't change at this transition? So let's suppose in this example that this region here is some less conductive material, still a conductor, but less conductive, more resistive, so that the conductivity of material 2 will be less than the conductivity of material 1. All right, let's set up the Nevada equation. So the current entering into region 2, that can be given by our current density times the cross-sectional area of our wire. And the Nevada equation says how that relates to our number density and our fundamental charge and our drift velocity and our cross-sectional area. And we also know that in steady state current, this must be constant. So the current entering that more resistive material must be the same as the current exiting that more resistive material, so that we don't have a buildup of charge inside this region here. All right, so the current in equals the current out, which implies that, let's see here, since let's see, if we applied this equation here to both material 1 and material 2, then these values for material 1 equal these values for material 2. And if the cross-sectional areas are the same in both, so that the thickness of the wire isn't changing, and of course little e is the same in both regions, then what this means is that the number density of electrons in region 1 times the drift velocity in region 1, that has to equal to the number density of free electrons in region 2 times the drift velocity in region 2. That condition must hold to guarantee that the current entering is the same as the current leaving, or rather, the current entering this way is the same as the current leaving that way. All right then, so if this material has a higher concentration of electrons in a given volume, let's say, so if Ne2 was higher than Ne1, then that means that the drift velocity of our electrons must be lower in this region than in this region. So we can achieve the same current in both materials by even if we have electrons packed more tightly in here, just by having the electrons in here drifting at a lower velocity. Let's apply Ohm's law then. So the current density is related to our electric field. Let's see here. If the current entering and leaving must be the same and the cross-sectional areas are the same, then this implies that our current density in both materials 1 and 2, is also constant, which tells us that sigma E in region 1 must be equal sigma E in region 2. So the conductivity in region 1 times the field strength in region 1 equals the conductivity in region 2 times the field strength in region 2. So in our example, if region 2 has a lower conductivity, if the conductivity here is lower because this is a more resistive, less conductive material, then the field strength in there must be higher. So it must be the case that we have a stronger field in region 2 than region 1 if region 2 is less conductive. That'll lead us into our next question. What is it exactly that creates the stronger field in the more resistive medium?